So thanks for the introduction and for inviting me here. And in this beautiful city, which will be my city in a few months, and I'm looking forward to it. So I will start by a general introduction about the derived category, and then I will move to understanding what its relation or conjectural relation with birational transformations. So, I mean, derived category is quite an abstract gadget, and I would like to give a very hand-waving introduction on why do we work with the derived category, and what could be some sort of insight about the reason why in algebraic geometry of smooth projective varieties over C, we might be interested in looking for some sort of geometry inside the derived category, or some sort of geometric information coming from the derived category. So what do we do in algebraic geometry? We often study cohomology of sheaves. I mean that many pieces of information we are interested in when we do algebraic geometry are captured by the cohomology of sheaves. And well, sometimes we have simple sheaves like homogeneous vector bundles on rational homogeneous varieties, and we can just compute cohomology straight away with some theorem. Sometimes we don't have these tools, but we have to, find a slightly less direct way, which is by using resolutions. So to compute this, very often we use resolution. So there are many examples of resolutions we typically use in algebraic geometry to describe cohomology of sheaves. Like for instance, if we consider hypersurfaces of degree d, say, in the projective space, let's say Pn, and let's call this embedding here I, then we have that we might be interested in studying the structure sheaf of the string. So we just use the usual. Okay, so the usual ideal sheaf sequence where we have the structure sheaf of Pn, and here we have Pn minus t and t. So we use this exact sequence in order to compute the cohomology of this. Those two objects here are like bundles on the projective space. So we know everything about them, and then we get this. Or a slightly more complicated but still quite simple example is the zero locus of a section S of a vector bundle on a smooth projective variety X. And of course, we want E to be globally generated and section to be general, so that everything is smooth and expected codimensional, which is what we want. Then we want that if we call, let's say, Y the zero locus, and we call I again the embedding inside the variety X, then we have the causal sequence, which is something like this. Determinant of the dual, then we have wedge R minus 1 B dual, where R is the rank of E. Then you know how it goes. We end up with wedge 2 B dual, O, and then we have I push forward of O of Y. Okay. So actually, the cohomology of those sheaves comes directly from understanding the cohomology of their resolutions and moving to long exact sequences of cohomology. So applying the derived global section functor, actually. So, this can be made slightly a bit formal if you consider the following thing. So take a resolution of a sheaf F, and let's write it like this: C1, let's say C1, C2, Cn, okay? And then we have F. Let me write it like this, okay? So this is the resolution. I wrote it like this because of the following reason. If I write a 0 here, this stops being exact. It becomes a complex, right? Your general complex, which is not exact anymore. It has some homology. And I call F a complex just by putting zeros everywhere here. So this F together with zero maps everywhere else, defines a map of complexes. And this map induces an isomorphism at the level of homology. So its map at the level of homology is an isomorphism. And this is called a quasi-isomorphism. ISO, usually called. So what is the derived category? It is the perfect framework where we can trade complicated sheaves like F with complexes of simpler objects. So we want a category where we can freely identify up to isomorphisms in this category, sheaves with their resolutions. And on a smooth projective variety, every sheaf, every coherent sheaf admits a resolution of vector bundles. So actually, we are translating the problem of computing homology of sheaves into computing homology of complexes where every term is a vector bundle. So it's definitely similar. So the slogan, let's say, which I do not dare to call definition because I'm very much hand-waving, is the following. So the derived category, let's say the bounded derived category, of coherent sheaf let's call it d of x for x smooth projective. Okay, is given by the following. Objects will be complexes of coherent sheaves. So objects and morphisms, what will they be? I mean, the first thing we can think about is just morphisms of complex sheaves. Sorry, morphisms of complexes of sheaves. So maps of complexes. But we want the additional condition that quasi-isomorphisms, that's called Q isos, are isomorphisms in the category X. So quasi-isomorphisms in the category of complexes will be isomorphisms in the derived category. So if you just try to work with this, you end up with a problem. Because when you just try to write down what a morphism could be, you end up with some weird stuff, actually. So assume you have a complex H, for instance, and a morphism of complexes towards say G. Okay. Then assume you have a third complex. Let's call it F. And assume that you have a map from H to F, which in the category of complexes is a quasi-isomorphism. So let me write Q iso. Okay. So in the derived category, those two guys are isomorphic. So if you have a map here, you also have a map from here to here. So if you want to define a morphism in the derived category, you need the data of a third object and a morphism here in the category of complexes, and quasi-isomorphism here, still in the category of complexes. But still, if you try to work out composition, you end up with an additional problem. Because let's say you have another object here. Maybe I should try to make this diagram a bit less. So H now is here. This is Q iso. And I have, I don't know, I here, J, and yeah, something like this. So a morphism here will be something like this in the derived category. But then, since it is a category, I want the composition to be a morphism again. So what does it mean for the composition to be a morphism? It means that I need an object up here, okay, with quasi-isomorphism here, morphism here, such that the big triangle is indeed a morphism. Problem is that in the category of complexes, you can't always find this. It doesn't necessarily exist such that this diagram commutes. So you have to move to the homotopy category of complexes of coherent sheaves. where you actually work up to homotopy equivalence. And that's the reason why you have 30 pages on the book of Albrecht to understand actually that this kind of thing is well defined instead of just translating through that. So, I mean, yes.
You can just define morphisms as arbitrary length of zigzags.
Yes, because every time you do that, you can find other objects and morphisms such that you can complete the big triangle.
Yeah, but is it necessary to impose that you can complete the big triangle? Can you not just say, okay, a morphism is a zigzag of arbitrary length?
A zigzag like that. Well, if you do that, then you need to have. So this has a morphism to this, so it needs that. It means that. So let me think. So if you forget this guy here, and you assume that you can define a morphism just by an arbitrary zigzag, I don't know. Definitely something must go wrong.
Okay.
But I don't know what.
The general problem is that it becomes so unwieldy to work with. So
okay,
restricting to the setting where you can.
Okay, so maybe it's what you're saying is homotopy equivalent to what I'm suggesting, but this is a better model.
Yeah.
That's possible. That's possible. That's possible.
And also, those are some size issues.
Okay.
You would get classes of morphisms, subsets of morphisms.
Okay.
Oh, I see. So you can really. Okay. So thanks. Okay. Any other question? Okay. So actually, this kind of thing looks very abstract, and it is, but it contains a surprising amount of geometric information, actually, because I mean, if you study different kinds of varieties, you find that there are several nice properties which relate the derived category of those varieties and their isomorphism class or homological data or something like this. So, for instance, if you take X smooth projective and you want that the canonical bundle or the anti-canonical bundle is ample. Okay, so either Fano or general type, either general type or Fano. Then you have a very deep theorem which says that X is isomorphic to a second variety Y if and only if the derived category of X is equivalent to the derived category of Y. So you have an equivalence of categories like this. And this is called the reconstruction theorem by von and Orwell. Yeah.
Sorry, maybe I missed it, but is the condition that you place on X that omega X or its dual is ample, or is it always true?
No. You assume that you have a smooth projective variety with this condition.
Okay, yeah.
Either this or this condition.
Yeah.
Or maybe I should write it such that here.
Yeah.
Smooth projective, okay. Such that. Okay.
Thank you.
Okay. Yes.
I wonder about the statement. Is this really one statement, or are they completely different proofs for the Fano region and the?
No, it's the same kind of statement. I mean, I think it's the same kind of proof that you use. Yeah.
It just uses the incidental line bundle, or does it reuse that it's the anticanonical one?
You use the canonical or anti-canonical one because the canonical bundle on the smooth projective variety defines an important autoequivalence of the category, which is the third functor. So I think that they define the equivalence going in this direction. No, sorry. They define the isomorphism, so this direction here. This direction is trivial, of course, but the other direction, I think they do it by associating to every point in your variety some object in the other variety, some kind of sheaf that then allows you to do this basically. So I think that the proof is the same for canonical or anti-canonical because it comes from the third functor. I'm not sure.
Is it something naive, like looking at where skyscraper shapes go, something like this, or?
The idea is something like that, but it's totally not trivial. But the idea is something like that. You want to construct some object coming from the ideal by the structure sheaf of points, basically, like this. But it's not a trivial solution. Okay. So then you have this result for smooth projective funnel general type varieties, and basically this tells us that the derived category is an invariant up to isomorphism, which is quite a powerful thing, actually. But then, if you consider K3 surfaces, let's take two varieties, X and Y, and assume they are K3 surfaces, then you have that there exist situations where they are derived equivalent but not isomorphic. In particular, you have that the derived category fixes some kind of homological data. So in particular, you have some lattice associated to the H2 homology of this variety, which is preserved up to isometry if and only if those varieties are derived equivalent. So this is called the derived varieties theorem. And it's due to Mukai and Orlov. Okay. Then one can think, well, here we have that the derived category fixes the isomorphism class. Here it doesn't, but it still fixes some kind of geometric data. What about higher dimensional Calabi-Yau varieties? So X and Y, Calabi-Yau, dimension bigger than 2. Here it fails spectacularly. I mean, everything that could go wrong goes wrong, actually, because you find not only pairs of varieties which are derived equivalent but not isomorphic, but even not birational. So you can find examples such that X and Y are not even isomorphic out of codimension 1, but they are derived equivalent. Okay. So this kind of examples are not exactly super common, but they can be constructed in several ways. Like for instance, you can find those kinds of varieties if you try to intersect the Grassmannian G25 inside the projective space P9 with a translate of it. Like you move it with an automorphism of P9. So the Grassmannian G25 lives in, G25 lives inside 9-dimensional projective space. If you act with an automorphism of this, you're moving it inside. So you can consider intersections of G25 with the image of G25 to a general automorphism. You can construct suitable pairs of those kinds of varieties, and there are Calabi-Yau threefolds if those kinds of maps are general. And you find pairs of such Calabi-Yau threefolds which satisfy those conditions, for instance. But you can construct these kind of examples also in different ways. So at this point, since we have different kinds of behavior for different kinds of varieties, what is the goal? The goal is to find the birational maps which preserve. So apparently, so what we want to do basically is to, let me try to erase. So what we want to do is to try to find some class of birational maps which preserve the derived category. So which induce a derived equivalence between the two varieties. So so let's have an example of.
Can I ask you before you go into like a naive question? So this dx picks up the dimension?
Sorry?
Can you have two varieties of different dimension having the same derived category? No.
No, that's
so you can extract the dimension.
The dimension is preserved by derived equivalence. So let's try to write down an example of a birational map which preserves the derived category. So you can consider a situation like this, where you have a variety x, so it's projective, and a variety y. And you define this map such that it is resolved by a blow-up of an inner space, called projective space, such that the exceptional divisor is a product of projective spaces of the same dimension. Okay? So to do that, you want to impose a condition on the normal bundle of this guy. You want the normal bundle to be a direct sum of all ones, and then you have that the projectivization of the normal bundle, which is the exceptional divisor, will have this form. Then you have that you can resolve this by another contraction, which gives the other factor. So it would be a blow up like this. So this kind of thing is called an Atiyah flop, or a standard flop. And Namikawa and Kawamata proved that this kind of flop induces derived equivalences. All this. Okay. So why did I consider this specific example? Well, you can look at this and try to compute the pullbacks of the canonical classes of those two guys. I mean, you compute twice the canonical class of this guy. You compute it once with respect to this blow-up structure, once with respect to this blow-up structure. With this kind of computation, you find out that the pullbacks of the canonical bundles of x and y are isomorphic. So you have the called P and Q, those maps. The pullback of omega x is isomorphic to Q pullback of omega y. Okay? So this observation leads to some kind of other observations, like you know that the canonical bundle, as I mentioned before, gives you, for smooth projective varieties, some nice autoequivalence, which is called a star functor. And it's a general result that equivalences of derived categories of smooth projective varieties preserve or commute with the star functor. So one can wonder, is it maybe true that every time we have a birational map resolved by a third variety like this, such that the pullbacks of the canonical bundles are isomorphic, then we have derived equivalence? And this is a very important conjecture, yeah.
So for now, I don't think we have seen a case where two varieties are not derived equivalent. So can you give an example of two varieties that are birational equivalents but not derived equivalent?
Yeah, irrational variety and PN, something like this, for instance. Irrational variety and a projective space of the same dimension, I guess. They are not necessarily derived equivalent. Yeah, I think if I
Is the derived category of Pn, is it easy?
Yeah, the derived category of Pn is basically you can write it in a very nice way if you consider semi-orthogonal decomposition. So I will get to that slightly later, but I can just give an idea. So sometimes you can generate the category of a variety with a finite number of objects. And for Pn, they are the simplest one possible. So like the derived category of Pn, let's say of P2, or like Pn is fine, can be written in terms of O of 1 up to O of n. So every object in this category can be written in terms of resolution such that you can split them in cones in which the cones are, in triangles in which the cones of the morphisms are objects like this. So in other words, you can generate them by resolution made by those kinds of objects. So yeah, it's the simplest possible. So, by the observation I made before, it kind of follows this kind of conjecture, which is the decay conjecture, so like this. By Mondal, Orlov, and independently by Kawamata. Okay. So what did I say? Actually, assume that we have a birational map such that there exists a variety Z with morphisms, or let's say resolved by a morphism from Z to X, let's call it F, and the morphism from Z to Y, let's call it G, such that the pullbacks of the canonical bundle are isomorphic. G pullback omega Y. Then this conjecture says that the derived category of X is equivalent to the derived category of Y. Okay, so I mean, why the decay conjecture? Because this can be summarized as K equivalence implies D equivalence, where K stands for canonical and D stands for derived. So what is the problem? I mean, what is the fact that makes this kind of conjecture an open problem until now? So the fact is that, I mean, the condition on a birational map to be resolved by a third variety which has this property is quite general. You can have very wide birational maps which satisfy the property. Like for instance, instead of having a single blow-up from here and one from there with the same exceptional divisor and so on, you might have multiple blow-ups of singular subvarieties, something like this, and cook them such that you can satisfy that. So it's quite hard in general to understand how to prove it. So actually what we want to do is to find the class of K equivalences, which are those kinds of maps like that, which preserve the canonical bundle, such that a class which is simple enough so that you can understand it at the level of derived categories, you can do something, but general enough such that it covers most of the interesting examples you have. So you want it to be big enough to give you actually a glimpse on what happens or what should happen in general. So one candidate for this kind of class of K equivalences is the following. Simple K equivalence what does it is a K equivalence such that okay, it is resolved by a single blow-up single blow-ups of smooth subvarieties on each side. Okay, so something like this. You have X, you have Y, you have, say, SX, which is the center of one blow-up, and you have SY here, and you have your blow-up, common blow-up from here, which we call Z. This map is called B, and this map is called Q. So there's a fact which comes from this, which has been proven by Lee, and it says that you have that the two exceptional divisors coincide. something similar to that, right? You have one variety here, exceptional divisor E, which maps down to here and to here, something like that. So E is a nice variety which has two projective bundle structures. Why? Because it's the projectivization of the normal bundle of Sx, but also the projectivization of the normal bundle of Sy. So it has two structures as projective bundle. And we have a line bundle. Let's call it L, such that what? L restricts to 201 on the fibers of both the projective bundle structure. So on each fiber, on each side. Let's try it like this. Okay, so this is just, those are just consequences proved by Lee that actually come from assuming that a K-equivalence is resolved by smooth blow-ups on both sides. But then can need to prove something more about this kind of constructions. Okay.
I'm sorry, quick question.
Yeah, of course.
Do you need to assume that this Z also has the condition about the pullbacks of the canonical divisors, or is it automatic that if one resolution is a K-equivalence, then any resolution also works?
Do you ask if in this diagram I am assuming that the pullback of the canonical bundles are yes, I do.
And could it happen that there is it is a K-equivalence,
Yeah.
and you can resolve it by a single blow-up, but you cannot resolve it by a single blow-up, which is also which also satisfies this, or it's.
Do you mean simple blow-ups from both sides, but without this condition here?
Even though there is also a resolution that satisfies this. I mean, maybe it's a good question.
So if you're blowing up something else, I think that if you blow up singular varieties, it doesn't happen.
But you don't have to assume it, right? I mean, the canonical of Z is the pullback of X plus the exception.
Right.
Which
if you
is
write it
also
like that,
the pullback of Y plus the
So
exception.
if you write the canonical of this, it will be just the pullback from here, and you have a multiple of the canonical from here.
Maybe you need to show
Same thing from the other side. No, but then you have to assume that the canonical of this and the canonical of this up here are isomorphic, and that you get that the pullback of the class of the canonical from the class of the exceptional divisor from this blow up is a multiple of the class of the exceptional divisor from the other blow up. And then by the fact that you have projective bundle structure, Lee concludes the theorem like that. But I don't think it's automatic. So what did you think it was automatic?
No, I think it's like the K equivalence condition that the pullback of the canonicals coincide on Z follows from the fact that such a diagram exists simply, that you have two blow-ups with common center. With common exceptional device.
The center is common, I agree.
No, sorry, with common exceptional device.
Then yes. Because
I don't think you need to. I think, I mean, I might be wrong. Yeah,
maybe you need that those two guys have the same codimension. That's probably you need. Otherwise, you get one is a multiple of the other. Something like that.
So the question is time.
Okay. Anyway,
Yes, right.
So what was I? Oh yeah, the theorem, but you can use it. So in this setting, you have that there exists a vibration, let's say phi, from E to some smooth projective base B. Okay, such that it's locally trivial, or with it one fibers. Okay, with fiber F such that, first of all, F is a Fano variety of bigger than 2. And it has 2 projective bundle structures. So F has 2 projective bundle structures. Okay. And L restricted to F. L was the bundle, the line bundle you have here, such that it restricts to the relative O, I mean, to the O1 if you restrict to a fiber from here or one fiber from here. If restricted to a fiber, okay, then it restricts to O1 on each fiber of the projective bundle structures of F. Okay. So basically, I mean, why am I stating this theorem? Because basically it says that E has a vibration over a smooth projective base B, which enters through this side or this side of the diagram commutatively. That's another way to see it. And the fibers of the map from E to B are very special fiber varieties, bigger than 2 projective bundle structures, a bundle which is the O1 on both sides simultaneously. And this is quite interesting because all the examples known, except for one of those varieties F, are rational homogeneous. So they are quotients of simple Lie groups by parabolic subgroups like Grassmannians, flag generalized Grassmannians, this kind of things. So you can study them with some representation theory. That's the nice thing. And they're all classified. So except for that one example, all the possible Fs that you can get from a diagram like this are classified. So you know quite a lot about simple K equivalences, except for that example. There's no actual proof that the only non-rational homogeneous example is the only one in general. There might be some other possible examples, but so far, no one found one actually. And it seems that the existence of this particular example is quite related to the geometry of a very specific setting, actually, which appears only in one specific dimension. So it's quite unlikely that we can find another one. So this last observation that I made motivates the following kind of, maybe this diagram was important. Oh no, that one is the important one. So this kind of observation about the fact that basically all the examples we know except for one are homogeneous and thus classified justifies the following definition. So a generalized Grassmann plot is a simple K equivalence such that F is rational homogeneous and pi is this map here, okay? It's a composition of those two maps or those two maps, okay? Is a generalized flat bundle. So what do I mean? I mean that, you know, you have Grassmannians, you can also construct Grassmann bundles. So instead of parameterizing subspaces of a linear space, you have a vibration over a base, and every fiber is a space variety parameterizing linear spaces in the fiber, something like this. So it's a vibration, it's a locally triggered vibration where all the fibers are isomorphic to a Grassmannian. But you can do that not only with Grassmannians, you can do it with every homogeneous variety. So this kind of things are called generalized flag bundles. So we can call them relative homogeneous varieties if you want. Okay. It's quite simple. If I give you an example, you can consider an example where f, I will refer to this diagram here, okay, and the notion of f that I wrote there. You can assume f to be, I don't know, the flag variety f1 n-1 n, which is a variety that parameterizes pairs of a line and an n-1 space, such that the line is contained in the n-1 space. Everyone contained in this n-dimensional space. It's an incidence variety of line and hyperplane in a affine space of dimension n, if you want. In this case, you have that E will be the flag bundle of 1, n-1, and E for, oh, let's give it for a name. Let's say T, where T is a vector bundle over B. So you fix a vector bundle, then you can construct, on any B, you can construct this kind of flop by just having a diagram like that, such that E is this kind of flag bundle. Okay.
Yeah. So what is the sort of the easiest example of a standard flop? To have a, because this is an example of a generalized Graham flop that is not a
this is the Mukai flop over a base. Yeah.
Okay. Yeah.
Yeah. Sorry, you were asking an example of.
Yeah, sort of the toy baby example where this, you know, that this generalizes. You know, sort of you have P1 cross P1, then on one side contracts one, on the other, like sort of you know, to see what you are generalizing.
Yeah, for instance, you can consider a situation where instead, yeah, before I gave the example, the one I raised here was given by the situation where you blow up a projective space from one side and an isomorphic projective space from the other side. If instead of blowing up projective spaces, you blow up projective bundles over a common base, you get that. But instead of having this as exceptional divisor, you have a fibration with fibers isomorphic to Pn cross Pn, which is not the, it's not the product of projective bundles, but the fiber is a product of projective spaces on the same basis. So you can get it like that, for instance. This one generalizes a different flop in which you blow up projective spaces, but the normal bundle is the tangent. So you get a smaller exceptional divisor, which is an incident variety like this. Okay. So let me spend just a few minutes to say something about the evidences of this kind of conjecture applied to this, because I mean the plan is, now I described you a very nice family of flops, a very nice class of flops, which are the generalized Graham flops. So let me say a class of K equivalences. And what we want to do is to test the decay conjecture, that conjecture about K equivalence implying D equivalence, on those kinds of flops. So we have some evidence. So first of all, there's I can call it a theorem because I will state it very informally, so let's call it a fact. We have that one can prove derived equivalence with a technique which depends only on the fiber F. So this means that if you know that derived equivalence holds for a birational map like this, for B equal to a point, then with some assumption on the proof you have, so you need some technical assumptions on the computations you do actually, then it holds for every B smooth projective. Because you can kind of relativize the construction. you apply. So what you do is just work with flops where B is a point, and forget the Grassmann bundles, the flag bundles, and only work with flags, Grassmannians, homogeneous varieties like that. So, for instance, if F is the G2 complete flag, so you take the simple Lie group of type G2 and you quotient it by the minimal parabolic subgroup, then you have derived equivalence of the associated flop by Hutzenson and by Weda. Then if you take F to be Pn plus Pn, or the flag variety 1 n minus 1 n, these are respectively the standard and n flop. And these we've been seeing them before, but they are due to Kawamata, Namikawa, okay, and also Bondar and Orlov have a proof. Okay. Then if you take F to be the flag variety F1, sorry, not this, but 2, 3, 5, you have a proof by Kapuska, myself, and Morimura. Then if you take F to be the orthogonal Grassmannian OG410, it's just another homogeneous variety. Then you have it by the paper of myself and C. Okay. And the last case we know is C2 mod P12. Okay. Yeah. And here this is due to sigma. Okay. So all those cases look like just a handful of cases, but whenever we know the proof for those, you can generalize that to every base B. So actually we have infinite families of different cases. So how do we prove this? Let's try to do it in 10 minutes. Wish me luck. So, I mean, the idea is quite simple. Is that basically you use the two blow-up structures. This should stay here. So we use the two blow-up structures to write the derived category of this guy here, C, in two different ways. So what we need here is a theorem by Orlov. So first of all, I have to say something like this. So a similar formula decomposition is a collection, let's say of what? A similar type of decomposition of, let's say, the derived category of a variety X is a collection of subcategories. Let's say A1 up to AN of subcategories such that you have two conditions. You have that you have no morphisms from objects E to objects F, such that E lives inside the component AI, and F lives in the component AJ, and you also have I bigger than J. So in other words, you have no morphisms in this direction, from objects in a given subcategory to objects in one which lies before. Okay, so it's an ordered collection. And also you have this, here I will translate a bit more, even more than usual. I say that AI, this collection, generates the whole category. And it's like what I said before for the category of the projective space. In that case, all the subcategories are generated each by a single object. Generates the whole category means that every object in the category dx is given by a solution in which each term can be constructed by those objects, by elements of those objects of those subcategories here. Or in other words, the X is the smallest category clause with respect to homes which contains all of them. You can see it also like this. So I introduced this because here. Because sometimes, I mean, quite often you have that some maps of varieties come with associated semi-orthogonal decompositions. And this is quite an interesting thing, especially for us who want to work with blowups, because we have a theorem by Orlov, which says, okay, which says this, that if we have a blowout, say E inside Z X and the center is S, okay, we want this to be a blowup. And yeah, let's call it P. We call P bar this map here, and I is the embedding of the exceptional divisor. Then this comes with a semi-orthogonal decomposition. So we have that dz is given by I push forward of P bar pull back the S times O of minus R plus 1. This line bundle is like the O minus R plus 1 relative with respect to this projective bundle structure here. Then you have other copies of the category of the S embedded in a different way. In particular, you have I push forward. Plus 1 is I push forward of P pull back of the S times O of minus 1. Okay. And then you have the pullback of this with respect to P. So this means that you have that the category of this has a semi-orthogonal decomposition in which you have several copies of the category of this embedded like this. You pull it back here, you twist it by the relative O minus something, and then you push it forward here. And then at the end of all this sequence of subcategories equivalent to this, then you have the pullback of the category of the base. So for us, you can do it twice, because you can do it either using this block structure or using this block structure here. So what we get is something like this. D of Z will be given by a sequence of categories x1 over x1, x1, P pullback of x, so this is type x. Or we can use the other blow-up structure, and we have something like this: y minus y plus 1, y minus 1, q pullback of y. Okay, where we have that all the x's are equivalent to the category of Sx, and the y's are equivalent to the category of Fy. Okay, because of the blow-up thing that I showed there. But then we have that the fiber of this map and also the fibers of those maps are fibrations. They are relative Grassmannians actually. And then if we have an exceptional collection on the fiber, here I'm hiding some deep results actually from Samokin. So let me at least hold it too. We have that each of those chunks can be generated by a list of objects, a finite list of objects. So what we end up with is something like this. We end up with D of Z given by E1 times the category of B up to E, say, N, for some N, times the category of B, and then the pullback of the category of X. And similarly, we have the same kind of expression with different objects, but the same number of objects from the other side. So F1 times d of b up to fn times d of b and q pullback of dy. So now, two things. First of all, if we didn't have db anywhere, but we just had a sequence of objects, then we could try to transform one of those sequences into the other one, keeping this category here or transforming it to an equivalent one. This technique is called mutations of exceptional objects. Basically, you exchange the order and you change one of them into a different one, which keeps the set generating for the category. It's something which gets quite simple to do if you find the right sequence of those transformations, if you're working with homogeneous vector bundles, so simple vector bundles from homogeneous varieties. And that's actually what happens if we have all the assumptions there. The second thing that we have to consider is that it's possible to prove, because of the symbol structure of those vibrations, that the operation of transforming, exchanging those bundles, commutes with the tensor product by this category of the base B. So this is the reason why, if it works for a point, it works for every B. Because when you have this kind of conditions, when you have this kind, of setting, you can prove that under my hypothesis, on some computational stuff, actually, you can make the tensor product with the B commute with this kind of mutations. So you end up with something like this. You end up with, I go here. So after this kind of sequence of transformations, let me call them mutations, which is the name, you end up with something like this. dz will be given by E1 times d of b up to En times d of b and e pull back d of x, but also mutating the second one, because we kept this one like this. While on the second one, we acted by transforming this collection until we find the same sequence of objects. E1 times dB, En times dB, and then you have some equivalence factor applied to Q back of Dy. But then you have that since those two guys are the same orthogonal complements of the same category, they must be the same category as well. So it means that this one, the category of X, is equivalent to the category of Y, if we are able to do the mutations, which happens to be true only in the cases so far that I listed before. So yeah, basically this is how we've improved this. It's not the only method you can use, but I think it's the one which can work for most cases like this. And it's all a matter of trying to find the right sequence of transformations. I think I can stop here.
Other questions?